Hello and welcome to Logos Research Associates live stream broadcast. I'm John Baumgardner, and it is my privilege to be your host for this presentation. Logos Research Associates is a fellowship of scholars and scientists who are committed to upholding a high view of Scripture and a high view of science. The goal of this live stream series is to provide you with the opportunity to hear from top researchers who convey cutting-edge scientific evidence for the creation account of Earth history. Before I introduce our speaker, let me open in a short prayer, if you'll please join me. Heavenly Father, we thank you that you are the creator. You're the mighty God who brought this all into existence by your power. And we thank you for the privilege of looking at more details of how you created and what you created and the evidence for that. Father, thank you for our speaker tonight. Pray your Holy Spirit might enable him, empower him mightily, and open our understanding and give us new insights to the wonders of what you've done. So thank you. We give you praise in Jesus' name. Before I let me just now introduce our speaker. He is Dr. Mark Horstemeyer. He's a distinguished professor at Liberty University, and he served for 6 years as Dean of Engineering, just recently retiring from that position a few months ago. He also has 35 years of experience at Owens Corning Fiberglass, Sandia National Laboratories, and Mississippi State University. He is a fellow of the American Society of Mechanical Engineers, a fellow of the American Society of Metals, also of the Society of Automotive Engineers, and also of the American Association for the Advancement of Science. He has published over 600 journal articles, conference papers, books, and technical reports. And notably, he has mentored over 200 graduate students and postdoctoral researchers. So let me welcome him now to share with us. His topic is reverse creationeering, a framework for conducting creation science. Welcome, Mark.
Thank you, John. Can you hear me okay? Can you hear me okay?
I can hear you fine.
Can I get confirmation that you can hear me, John, or no?
Yes, I hear you well.
Okay. So thanks, John, for introducing me. I first met John in 1991, so we've been working together for about 34 years, and I appreciate him asking me to come on and talk about this topic. I have to be honest with you, this is actually a recent topic of mine, and I would actually categorize myself as more of a scientist than an engineer. But this idea of reverse creationeering, first of all, let me talk about creationeering, and I'll repeat myself about 3 times in this whole presentation so that you might get a good takeaway point. The word engineering comes about from these catapult engines, the catapults that were done for the military years ago, and the people that designed them, built them, and used them were called engineers. But the word wasn't really framed for society until Robert Fulton's steam engines. So the word engineers comes from people who study engines. And if you look at how many engineers around the world really work on engines, it's less than 1%. So it's a misnomer. It's really a bad word. So the real idea is creationeering. It's a creationeering process. And I use the word reverse engineering because there's a forward process of creationeering that I'm going to talk about, and you have to understand that first. Then I think it'll make sense to you as we try to conduct creation science, because when we do the creation science now, we're looking at now, and we're trying to figure out the past from now. So, I'd like to couch this in terms of the block to the left. The situation designates that there have been legal battles that we lost. I'm going to go through those in terms of creation or faith versus science. There's an internet paradigm about creation scientists. It's not good. It's very negative. Atheism growth has happened over the last 20 years or so at a pretty high rate. Deconstructing Christianity has been a wave that's gone through and motivated by an evolutionary paradigm. And then I would even say that creation science lacks the modern communication. And I'm going to review all that. And that sort of positions for the idea of why creationeering, I think, is the next strategic paradigm to be able to move forward with our community. Now, this creationeering paradigm, there is a science aspect to it, and integrated computational materials engineering, ICME as I call it, is important to that. What's ICME? It's basically multiscale modeling. In 1990, I worked at Sandia National Labs at the time designing thermonuclear bombs, and we weren't allowed to do underground thermonuclear tests, that the bombs, make sure the bomb's going to go bang when you want it to go bang. But we had to have a 10 to the 9th reliability the bomb's going to go bang. 10 to the 9th. That's the highest reliability I know of anything man-made that anything's ever done. So a nuclear plant's like 10 to the 4th. A car's like 10 to the 1st. So it gives you an idea of this. And when I say reliability, how this goes is, so we do an analysis on a material, and we get its material behavior. But there's errors with it. If we only do 3 tests, there's errors. 5 tests, there's errors. When you do 10,000 of them, there's no more errors. That becomes the uncertainty band. But we can't do that many experiments. So there's math that goes from the errors to the uncertainty. Once we have the uncertainty, we can go to the probability. Once we go to the probability, we know the reliability. Okay? So 10 to the 9th reliability bombs. How do you get there? You can't do an experiment. That's when we started multiscale modeling. Going from electrons to atoms to particles to grains, all the way up to large-scale structures and simulating this. That's multiscale modeling. The other aspect of this is dependence, history dependence. We have a framework that there's a word called internal state variables that capture history effects. You're a function of your history. I'm a function of my history. What happens next is a basis of our history projecting forward into that. We now have mathematical capability to do that. And it's able to live at a very high length scale, very high volume scale, that all these lower length scale things come into it, and it's able to sort of predict the future. And this is how we design things. I'm going to explain that. Also involved with that is this process where everything has a chemistry. You have a chemistry, that chair has a chemistry, a side door of a car has a chemistry, but it went through a process to get to a point. And that process, through heating and pressure and all that kind of, gives you microstructures or nanostructures or millimeter structures all the way through. And then those give you properties. And then those properties are used to determine the performance environment, what we're doing when it's actually performing. So that's the little blue box in the lower left-hand corner. But what this is done in the creationeering is involved with design. Now, you have all heard about the intelligent design movement. Those guys are mathematicians, physicists, they're biologists. Who are the people that learn design and educate in design? Anybody want to hazard a guess? Yes, it's engineers. And there's 3 aspects to every design. There's objectives, constraints, and variables. So the takeaway point for everybody online and in the room, I'm going to ask you to appropriate these design things. So when somebody says design ever, you should be thinking objectives, constraints, and variables. So for all the geologists in the room, or the astronomers, the biologists, the paleontologists, the chemists, or whateverologist, I want to challenge you to think about what were God's objectives, what were His design constraints, and what were His variables. That's going to be the goal at the end. If we do this, and if we move this way in this paradigm shift, which I believe it's moving from a shift from science to engineering, you will get a new idea, a new revelation of God's glory. It happened to me. I was 45 years old before I even started thinking about this. I'm 62 now, so I've been thinking about it, for 17 years or so. And I want you to understand that God not only created means design and went through the process, He also made it. Now, we have this word in the Bible that was translated by the King James people as creator. But that really only has one aspect to it. Creationeering has both the design and the making of the thing. And then finally, this K through PhD idea. Right now, there's no engineering curriculum kindergarten through through high school, through 12th grade. But if you can have these students, these kids understand that hey, a cake has a certain process and how it's made. A car has a certain process, and it's all the same process. The building does, the streets do. And they'll start really, everything was engineered, everything was creationeered. Everything. So then it's an easy thing to come that then not only every man-made thing, but everything that exists was creationeered by an intelligent designer God. So it's basically getting God back in the classroom without worrying about all the legal battles that we lost. So I'm trying to argue not faith versus science, but engineering versus science. Okay? So I'm going to go through all this. We're going to wrap it up at the end. And this background comes about with these sequence of books. When I first started this in the 1980s, focused on metals. And then from the metals, we went to polymers and then cementitious materials. And by the way, every person, like when first we did aluminum, then we started moving the idea of this multiscale modeling and using intrinsic errors to steel. They were saying, oh, you can't do that. Steel is different than aluminum. Well, we did it. Oh, then you can't do magnesium because it's hexagonal close pack. But we did it. Oh, and then we went to polymers. Oh, polymers are so temperature, so strain rate dependent. There's no way you could do it. Well, we did it. You can't do it for cementitious materials. We did it. So anyway, the idea came about in this 2012 book. In that 2018 book were all these examples. Then I even showed in 2021, wrote something related to the brain, the human brain. I'm working on something with the crater, the Arizona crater, right now to show that we could do this with rocks. Okay? But in the end, I'm hoping also to do this related to simulating Genesis. Simulating the days of creation using this, simulating the Genesis flood, the ice age after, and that sort of thing. All right, so the agenda I'm going to talk about is the current issues with the creation science movement, the idea of creationeering. I'm going to go through the example with a car, because I think everybody knows about a car and it'll make sense for you. Then I'm going to take that, appropriate that for the astrosphere, geosphere, and biosphere. And I'm finally going to make some recommendations. All right, so let's talk about the first issue with the creation science movement. And the first one has to do with these legal battles. And all these legal battles were constructed in the United States society, in the legal system of faith versus science. The first one started in 1968, where the teaching of evolution was allowed. We weren't allowed to prohibit it, okay, because of the First Amendment. That was 1968, Arkansas. Later, about 14 years later in Arkansas, it was proposed to teach creation science, but he says, no, it's religious. It's defined as religious, not science, by the legal system in our country. Not science. Okay? 1987, Louisiana tried to put forth something, and it struck it down that it cannot be taught in conjunction with evolution. It's legal in the United States of America. The last one in Pennsylvania, this 2005, the Federal District Court ruled that teaching intelligent design, now, not even creation science, but intelligent design, is illegal, is unconstitutional. Now there, they say intelligent design is not science. Actually, I agree with that. It's an engineering. So our group posed the wrong argument. And I'm going to show you today the right argument is engineering versus science. The second point, the internet calls creation scientists pseudoscientists. I just Googled this. Okay? Are creation scientists pseudoscientists? Yes! Google says yes. You look at YouTube, yes. You look at all the websites, yes. So this proliferation of this information or misinformation is going everywhere. And all the AI and machine learning algorithms, yeah, we're kooks. We're crazies. All right? You see the position against this? The next one is atheism has increased. If you look at the plot, this is a 2020 data gathering. And if you look at the atheists, 1980, 2020, it was 8% in 1980, 12% in 1990, 2000, or 16%, 20%, up to 23%. But even the non-practicing religion and even the non-religious, it's increasing, and the practicing religious people going down. These are big numbers, folks. This is the position of today. And this other issue, this deconstructing Christianity, I've been paying attention to these two guys, Rhett McLaughlin and Link Neal, the last 3 months, and I want to tell you how disturbing this has been to me. Very disturbing. These two guys grew up together in Christian families. They were young Earth creationists, grew up in a family. They married Christian women who were young Earth creationists. They worked for Campus Crusade for Christ. They did missionary work overseas. They are, by the way, the 5th largest moneymaker in YouTube videos. They're funny, they're comedians and all that. And recently, they talked about how they went from Christianity to non-Christianity, and it had 2.5 million viewers. They have over 3 million viewers on their YouTube site. Okay? And their first thing, they grew up creation scientists. They read the Hugh Ross book, Progressive Creationism, and they said, well, Christians believe this? Oh, well, and then they said, well, that doesn't make sense. But then they started reading all these evolutionary books. They said, oh, there's a different view out there. And they bought into that. And now, this deconstructive, it's very, very effective, unfortunately. It has affected my family personally, and I'm extremely disturbed by it. So, the last one. We have these Christian creation science books. We got websites, we got YouTube, we have the answers, but nobody reads them. They are boring, they're too intense, and it takes a PhD to read them. And every time I speak, and I've been speaking over 30 years on this, everybody says, is there any book written on that? I'm like, oh my word. Henry Morris, 1960, the Genesis flood. All these, they've never heard of these. How come they haven't heard of them? How come we haven't promoted these and communicated? Or are we not promoting and communicating in a better way? So this is the position. This is the position we're in right now. So here's Mark Horstemeyer's suggestion. Tactical methods, that means short term, we continue to do our scientific studies. But it has a local impact to the scientists and some Christians in the global. But we're already doing that, and look where we're at. The second one, continue having the ARC, the museums, homeschooling. Continue to do that. But look where we're at even with that. Better internet communications. We're nowhere near where we need to be with that. So strategically, I'm proposing to change the paradigm to proliferate our culture with creationeering. That's what I'm proposing as a strategic plan, long-term plan to affect culture and change it. We know the Bible says that God was an engineer, creationeer, before he was a scientist. In verse 1, in the beginning God created. That word created, paha, is something out of nothing. It's creating. Verse 4 is when he first observed and said it's good. An observation is something in the scientific method. Creating is something in the engineering realm. He was an engineer before he was a scientist. I'm waiting for the reaction online. Good, there's none. Isaiah 66:3. All these things my hand has made, the Lord said, and so all these things can be, declares the Lord. His hand was a creative, developed mechanism to make it happen. Colossians 1:16. All things were created through him and for him, and he's before all things, and in him all things are held together. So all things were designed by him, all things were made by him. There's two different aspects. Now, scientists, even creation scientists, are usually concerned with individual elements of the creation account, tend to only look at the single aspect of the design life cycle, whether it be a variation of species in biology, the formation of geologic column in geology, or the physics of starlight and time in astronomy. Without acknowledging the system interconnectivity and the purpose, we miss the bigger picture. All things were engineered, better yet, they were creationeered. Now, Theodore von Karman gave the best example in distinguishing features between science and engineering. He said, science seeks to understand what is. It's understanding what exists. And there is a process, a discovery process in the scientific method. We make an observation, a hypothesis. We develop the experiments for falsification. More experiments become a law. Engineering seeks to create what never was. He called himself a rocket engineer. All the community in the world called him a rocket scientist. In 1960, he won the first Medal of Science award in the United States of America. JFK, John F. Kennedy, the president, gave him this award, the Medal of Science. The process for engineering or creationeering, first step is design. And in design, you have objectives that you're trying to maximize or minimize, constraints and variables. The second part is analyzing the design, and this is where the science comes in. You use the scientific method to analyze this potential thing that's going to be your working hypothesis. And this is related to procurement. Procurement is whatever the material is. Then logistics, going and getting the things. The assembly of it once you get them. Its performance environment. The sustainability of that. And then death and recycling. So we put out this slide at every class at Liberty University in engineering. And creationeering has both the making the thing side. Proverbs 8:12 says it's a creator that gives you knowledge for witty inventions. It's a revelation from him to give you insight about making things. On the right-hand side, the business part, Deuteronomy 8:18 said it's your creator that gives you power to make wealth. So the idea is to make things, to make wealth for society to benefit it. And I'm not going to talk much on the business side, although you can go through the design and analysis of human resources, because God's interested in people. You can go through the finances. God's also interested in stewardship. About legal ways, he always has a moral law. Communication, sales, and marketing, and his management. He always has a structure. But what I'm going to do is on this left side, I want you to get this process. And I have quizzes in all the classes. You can ask these guys in the front row here about that. Now, I'm going to give you a second grade version of this so you always get it. We're going to bake a cake. We're going to design a cake. Okay? We're going to design it. What are the objectives? What do we want to maximize and minimize in a cake? Deliciousness. Okay, flavor. We want to increase or maximize flavor. Is there anything else? My daughter says beauty. She's a girly girl. She says beauty. Okay, so we're going to analyze it. Let's talk about deliciousness and maximizing flavor. What do you want? She always wants chocolate. And I say, what do you want? Okay, what about strawberry? No, we're analyzing it. What about vanilla? No, we want chocolate. Okay, how many layers? You got to have 3. 3 layers of chocolate, Nicole? Yes, 3 layers of chocolate. Okay. That's the objective. Procurement. What are the materials? What do the materials make up a cake? We need flour, we need sugar, okay, so on and so forth. That's procurement. Next step, we got to go get it. Logistics. Where do we get it? Kroger, Walmart, whatever. We get that. We come to the kitchen. We're going through an assembly process. We put it together. We throw it through a heat treatment process. Some people call that cooking, baking. Put that in an oven. Comes out, ready for performance. We look at it. We eat it. Were our objectives met? Did we maximize it? Did we like 3 layers of chocolate? Did it look good, these 3 layers? That's performance. We're eating it. Sustainability is, hey, that was way too much chocolate. We're going to make this better for next time. You know, there's way too much chocolate. We want strawberry, or we want vanilla, or we only want 2 layers. So sustainability is, how do I iterate this to make this long-term sustainable? Keep it going, make it better. And finally, death recycling. In this example, a little bit left over, give it to the goats. Okay, recycling. That's a cake. Now, that process, that's how you make cars. That's how you make rockets. That's how you make buildings. That's how you make chairs. That's how you make everything. Is that process right there. That's it. Engineering. You want your degree? Well, there's a little more classes you got to take. Okay. That's it. Do you know, in all, I have a bachelor's degree from West Virginia University, a master's degree from Ohio State, PhD from Georgia Tech. I worked at these places, Owens Corning Fiberglass, San Diego. Do you know nobody taught me that in engineering? The engineering schools taught me how to do science, not engineering. That's why I said I didn't know this till 40-some years into it. Now, let's go into detail. Let's look at this design. So in design, what we're trying to do, we're trying to have, like I said, objectives, constraints, and variables. This is my hope, your takeaway point. You're trying to maximize or minimize something like the cake. But what we're going to make a mathematical model on the picture on the left. So the minimum is in the well of that. There's a maximum related to it. So we're going to be able to use mathematics, which is our language, to be able to construct these design optimization things. And we're going to analyze it, okay? So that's design. The next step, analysis. Now, we use computational tools, and this example is like this Ford F-150 truck and running it in. So it's going through the scientific method. We have a design on this thing. We want to experiment it. Can it work? Can it not work? Okay? So that's analysis. The next thing is this procurement. What are the materials? What are the materials? And here's where this chemistry, process, structure, property, performance comes in. And this picture down on the left-hand corner was something that I laid out for the Nissan Altima side door, the Nissan Maxima side door, and the Quest van. They had a 6022 aluminum alloy. And first this was cast, that first step over there to the left, as an 18-inch cast billet in Wisconsin. It was then shipped to Smyrna, Tennessee, where it went through this hot rolling, the annealing, the cold rolling, and the final heat treatment, all the way down to a 1/4 inch. So it went from 18 inches as first thing to a 6-inch to 3-inch to down to a 1/4 inch. And the whole time its history is changing. The grain sizes are changing, the pressures, the temperatures are changing, and there's a multi-scale aspect. All these multi-scale features are changing as it goes along this history. Then it's shipped to Canton, Mississippi, and they go through this 5-stage stamping process. These are like Godzilla machines that are whumping this thing, and it's moving it around, and it forms it into the door. And then it goes to this painting, and the painting is heated so much the grain size grows again. It's amazing. It's that hot. Okay? Well, then what happens to the car? It goes through fatiguing, there's aging, and what if you crash this thing? Do you know most cars, before we put this in here, treated a 1-day-old car like a 10-year-old car? No history effects. We were the first ones to do that for the Nissan Altima Max and Quest vans. By the way, that's what we did with this is how we're designing nuclear bombs. So we're just transferring this that has this high reliability now to cars. By the way, we've done it for football helmets, and we've done it for other things as well, with different materials, with polymers. That's related to the procurement. Now logistics. Logistics is you got to go get the things. We send trucks to go get these parts from all over for a car. The assembly process is what Henry Ford made mass production happen. That there was an assembly process that was like ordered, and it was efficient, and it was timely. Then the performance environment. We all have cars, that sort of thing. This is a Cadillac control arm, and the Cadillac has 22 boundary conditions you're worried about, so that's 22 constraints. When we talked about objectives, constraints, and barriers, there's 22 conditions that Cadillac has to go through. And this particular simulation is a combination of panic, brake, pothole, strike. Those are two of the bad ones, and we put them together. You know, you get the big pothole if you're from Pittsburgh, Pennsylvania like me, potholes everywhere, and you panic, and you brake immediately, boom, and you get these kind of loads on it. That's the performance environment you're designing to. Okay? All right, and then sustainability. This is the Corvette, and this Corvette has a history. So they wanted to make the Corvette better, and every year. And that 2005 to 2013, that right there had the first magnesium engine cradle. We saved 70% weight saving. We used this exact method, multi-scale modeling, history dependence. We simulated that. We made that magnesium cradle for them. And from 2005 to 2013, that's what they had. It was just me and a master's student from Mississippi State. And they took it on, and they embraced it, and they got it. Sustainability. How do you get the next thing? And then finally, death recycling. Of course, this is a race car thing. This is not how you hope to experience death. I'm talking about the car, guys, not the people. All right? But I will say this, that every week in NASCAR, because we work with Hendrick Motorsports, they design a new car once a week for the next race next week. So they do nothing with those old cars. Once a week, they build a whole new car from nothing. But they have the process down. They already have their design down. They already have the procurement, the logistics, the assembly process. It's down. It's done. All right? So like I said, then there's also a business side to this that we're not going to talk about today because I want you to get the engineering side. Now, this car, this system, we're going to call it. It's the highest level macro-scale structure system, and it has a next level subsystem. And in this particular vehicle, there's 5 subsystems. There's the engine, transmission, drive, electric, body. Then there's modules. There's 17 modules below that, and then there ends up being 2,700 parts to this car. 2,700. Now, 27,000 in this part. There's 2,700 in our bomb. Now, the 1989 bomb. The current one, I'm not going to tell you. So the current bomb, the one 1988, 2,700, this had 27,000. The airplanes, the Boeing 77 has 270,000. But you see, you can't start from the lowest length scale and say, I'm going to build something from this one thing below. It starts from the top down. It's a downscaling anytime a design goes on. What are biologists trying to do with DNA, or evolutionists trying to do? They're trying to go from the bottom and they're trying to build up. You never get there. You never get there. We've never gotten there as humans. But you can when you start from the top and go down. Very important point. I hope you don't miss it. Now, how do you downscale? Because you always downscale before you upscale. Step one, there's a requirement of defining the information of the bridge. So you may be at a higher volume length scale and you're defining something for a lower length scale. So for the car, I have this, I have the full car and I have to subscale to the subsystem level. And it's going to give requirements, okay? So when I look at this, the constraints from the automobile level goes down to these 5 subsystems. It's defining things for them. It's defining the constraints. You're not allowed to do anything else. You have to live within this engine. It has to happen, because what if that car up there is a race car? The objectives are different than the Cadillac. You can't use a Cadillac in NASCAR. So when it goes down to the engine, it's going to be a different engine because of the above length scale that's defining the downscaling for you, all the way down. All right? So then you go down to the lower length scale. You say, now what do I do there? Well, that's when you analyze the cause and effect relationships. You do science at that length scale. And the effect, not all the causes go up. You just want the effect of the next highest length scale to go into there. You can't afford it. So this car thing, you know, if we do a crash and we put all the atoms in and we did simulation with all the atoms, there's a bunch of atoms that wouldn't care about that front end crash. They're wasted in there and they do nothing. So they're useless. Okay? So I want you to see this downscaling first. All right? And in each length scale, you apply the design aspect and the analysis and the procurement and the logistics and assembly. A lot of the problems with cars is assembly process because you're out of tolerance. You have the uncertainties, those errors, uncertainties, okay? Probabilities, reliability kind of thing you're trying to make better. All right, so this Cadillac control arm, I showed you a simulation of it, was put on the table in 1995. And at this point, we were only using this multi-scale modeling for bombs. We weren't using it for cars. So it was put on the table, and the question was asked at General Motors, where's this going to break? And the finite element stress guesser said point D. And all the material scientists said point B. They were both wrong. Why were they both wrong? Point B had the biggest defect up there in the upper left-hand corner. Okay? It had a big defect. But there were no stresses there in the 22 boundary conditions. The stresses were really low. Where, on the other hand, at D, they said, oh, that's the highest stress. But the material was perfect there. There was no pores. There was nothing there. It didn't break there. Where did it break? Point A. It's the combination of both the material science information and the mechanics from the boundary value problem, the 22 conditions of the boundary value problem. So the objective was to decrease the weight 25%. If we could decrease the weight 25%, and if that car had 25% less weight, it would make 85 miles a gallon. The Cadillac would make 85 miles a gallon. This year, the CAFE requirements for all cars to make 52 miles a gallon beyond this year. This is not talking about electrical engineering and Sparky and what Elon Musk is doing. This is just optimizing the material that's there. The second one was increase load-bearing capacity. The third was decrease the cost. So we went through a multi-scale modeling from electrons all the way up, called it from atoms to autos, went through design, went through optimization, algorithms, and on the lower left-hand corner, we showed where this thing would break, and we did the experiments 6 months later. I stood before 45 companies. I stood before Chrysler, Ford, GM. They're tier 1, tier 2 companies, and I said, it's going to break right there. They thought, you're crazy. Nobody's ever been able to predict that. But I had done all this before for bombs, and I had used that same material for a B-83 lead-on carrier. And they couldn't believe it. 6 months later, it broke at the exact spot. Do you know they stood up and clapped? And I was like, what? Why are you guys clapping? I said, we've never seen this before. Okay? Okay, but the goal wasn't just to be predictive. Remember, because we had the historic past, we were able to predict, because we have the history effects. It was actually to do this design optimization. And as it turned out, the curve on the right down here, where it says the load, the applied load versus displacement, the solid line is the load bearing before, and the one that's higher, it's 50% higher, that was the new optimized design, 25% less weight. Actually, the fatigue curve on the right shows it's doubled the fatigue life before it fractured, and down below it shows that we saved $2 per part. It was a $15 part. We made it $13. The same exact company, the same exact material. We didn't change the material at all. It was A356 cast aluminum. We just optimized the design. Okay? And we use this multi-scale process using the ISV, the internal state variables, and that's what I wrote in this book. And all these length scales were involved. And we downscaled to define the information on the bridge. Think of the Brooklyn Bridge. There's one scale that's higher, there's one scale lower, and the cars are going in a certain direction on the Brooklyn Bridge. But we can't take that Brooklyn Bridge and just put it in San Francisco and say, hey, that's the Golden State Bridge. No. The boundary conditions in San Francisco are different than New York. It's very different. So you define the bridge of information different from one length scale down below. And then you feed it up once you run the simulations. The DNA people, all you bio people, you're down below. You're about the third length scale from the bottom. The geologists, you're way at the top, looking at big rocks and structures. The astro people, you're way up. I'll talk about you later. All right, now, here's the point. At certain length scales, some of the things that happen here don't matter. In this study, we had Georgia Tech Material Science. We had, like I said, 45 companies, universities. And there's one guy that was saying, hey, you know, these little, they're 6% silicon. Sometimes they break, sometimes they debond. And he's looking at the microstructures on the scanning electron microscope, and he's seeing the differences. And he's saying, Horstemeyer, if you're going to model this at the top, you got to be able to capture that. And I thought, oh boy, that's complicated. So I had this Cornell student, undergrad Cornell student, and she ran calculations. And so we said, okay, let's just have it first debond. The little blue particles, that's the silicon particles. The white is aluminum, and the one hole is a casting pore. So we put in tension, and on the left you see the fracture pattern through that pore on the bottom, on the lower left-hand side. Okay? Then we said, what if it's just fracturing versus debonding? You're pulling it in tension now, or you're comparing. So there's those other silicon particles. The one either fracture, they just debond against the aluminum, and you say, oh, it's different. Look what's happening to that casting pore. The fracture path is really different than the one on the right, the one on the left. Can you see the difference? Hope so. Now, the real material had both debonding and fracturing. So we calibrated it, we fit it to the experiment, and we ran the calculations. The debond's on the upper right, the fracture's the lower right, and on the left we had both. You say, oh, it didn't even go through the casting pore. There was 6% of it went through those. So you see, it's very different fracture pattern. So I'm thinking, oh, he's right. He's right. The professor of material science, he looked at micron level, he looked at millimeter level, and he saw these differences. So Michelle, she ran the calculations, and she comes back and she says, Dr. Horstemeyer, they're all the same answer. I said, Michelle. So this was the damage level, it was true strain. The material only went to about 8% strain, so this is where it broke in real life. And I said, Michelle, I think you made an error. Go back and check your data. She came back, she did it again, and she goes, Dr. Horstemeyer, this is the same. Look. And I said, I think this is human error. It can't be. Look how different it is. And she was mad. And she said, you're coming to my desk, and I'm going to pull this data up, and I'm going to show you. And I sat there for 3 hours listening to her harass me. And she did. And she showed me this, and I said, okay, it doesn't matter. So I had to call that professor from Georgia Tech, and I said, even though you got all those beautiful things, they don't matter. They don't matter. 12 journal articles he had on this, and they don't matter. Now, I'm not saying everything from microstructure doesn't matter. I'm not saying your DNA tests don't matter. I'm not necessarily, but you got to be careful. Here's the point. I'm driving down the road, and I'm in a car, and it's windy outside, and the leaves come off the tree. A leaf comes off a tree, hits my car, I see it, and I move to the right. I saw a leaf hit my car and move my car to the right. I conclude that leaves move cars. Because that's what I saw. You have to be careful. Now, I showed you at the beginning, you have to join material science to the mechanics. So I'm not saying don't do that, but I'm saying you got to be careful about what degrees of freedom, what's important at one length scale here. Because some don't matter. Now, I'm going to come back to design, because this is related to the takeaway point. There's this guy, Wilfredo Pareto. And when you have more than one objective, it's called a multi-objective design optimization. So there's a set of decision variables that forms a feasible solution to a multiple objective optimization problem. It's called a Pareto frontier, a Pareto front sometimes. If there exists no other set such it could improve one decision variable without making at least another one worse. So there's a competition. So if I have two objectives, I get a set of possible solutions. And it's all these are possible solutions from one objective to the other. All right? Let's take an example of my finger. Let's say I want to design my finger. What's the objective I'm trying to minimize or maximize for my finger? Well, forget the cake. The cake had two, right? And the car has a bunch of... What about my finger? What's one of the max thing I'm trying to maximize? What is it? Strength. Okay, I want to maximize strength in my finger. Okay, what's another one?
Mobility.
He says mobility. Okay, let's just take two. There's probably more. These are all the possible solutions because there's two objectives. If there's three, there's three-dimensional space. If there's four, there's four-dimensional space. On and on. All right. Now the optimal solutions are the ones on this bottom line. All of those are possible optimal solutions. Anybody can pick. You can pick one on the lower right, upper left. It's still optimal. Okay? Not one solution. Now, there's 5 constraints, let's say. The first one says anything outside of that is you can't solve it. So for a car, it says, I can't go above this price. You can't make a car like that. So anything else, those are gone. You can't have them. Okay? The ones above, you're gone. If I'm doing a DNA study, I'm saying, hey, this is an elephant, I can't use a rhino. They're gone. Out. Okay? The second constraint, it's another one. So if it's a race car, I got some constraints on that road related to the boundary conditions. It's not a Cadillac going to go on that thing. If you've ever been to one of these NASCAR racetracks, they got big sides to them because they're worried about acceleration there. So now the solution space shrinks. Still multiple solutions. I add another constraint, constraint 3. I add another one, 4. It says anything to the right of that, no. Let's add one more. The 5th one could be a real constraint. But as it turns out, the solution set now doesn't care. So now, in this little space of optimal solutions, that's constrained my problem. But I have a problem now. I have a problem because there's all these different solutions in there. How do I get the right one? I get the right one when there's an intelligent designer on the outside, and intelligence has to pick the right one. By definition, if two or more objectives are in the design, by definition, it demands an intelligence outside the designed volume to pick an answer. I want that to sink in. If there's 2 or more objectives for any volume from the biggest to the smallest, and you can define those objectives, it demands an intelligence outside that designed volume to pick the answer. So, going back to the Pareto solution that demands an intelligent designer. In the Pareto front, as the number of parameters and design variables increases, the objective function, the objective, becomes more complex. It becomes complex. As the number of objectives increases, the number of solutions increases, and the objective function becomes more complex. This leads to an inordinate amount of options. And last, though, as the number of constraints increases, the number of solutions decreases, but the complexity increases even more. And this is done at every length scale. Very complex. Now, this is an example, actually, of a fairly simple solution. It's simple. Look at the mathematics of this. And all this, and it's a total cost versus an efficiency in a system that an industrial engineer would know. Now, so let's go back. So I talked about examples of this car going through these 8 steps: design, analysis, procurement, logistics, assembly, performance, sustainability, death, and recycling. And now I want to reverse engineer. I want to go backwards now that I know this. Okay? We know the history effects. So if you're going backwards, death and recycling, if you look at what's the objectives? Well, in the death part, we're not trying to have death, so we're trying to maximize safety. We're trying to minimize user rejection. We're trying to maximize end-of-life recyclability. There's objectives and constraints for this. If I go back to sustainability, how do I make this thing better? Now, the Toyota companies, Toyota, Honda, Japanese companies, they don't care about a 10 to 100,000 mile, 10-year limit, but the Detroit 3 do. So they're always trying to make things longer, better, and everything like that. Because their objective is better engineering. The Detroit 3, their objective is minimizing cost, maximizing profit. It's very different. So those different objectives drive different solutions. So sustainability, what are you trying to do? Safety, durability, aesthetics in terms of maximizing but minimizing weight. And assembly, you're trying to maximize quality time, minimize the time between putting things together. By the way, Nissan can make a car from design to building a car in 3 years. Ford's 5 years, GM's about 6 years, Chrysler 7 years. In 3 years, Nissan can do that from cradle to grave, from nothing. So logistics. For this particular part, you have casting for that 6022. It's hot rolled, annealed cold rolled, stamped. Logistics everywhere to finally get the 6022 side door. All right, so back to design and analysis. What are you trying to optimize or minimize, maximize safety, durability, fuel economy, consumer ratings, cost of production. There's 7 objectives in here, folks. What did we say if there's 2 or more? You need an engineer, creationeer, by definition, because there's multiple solutions. All right, so there's an example of a Ford Explorer cut corners in the procurement. It had problems. There was logistics problems with the space shuttle and assembly. It blew up. The sustainability of the Concorde jet was a problem, and so it died. The Titanic, there was no plan. They thought it was so indestructible. There was no design, no objectives, no constraints for death recycling. None. And you had a problem. So in engineering, we have to make things work. If you mess up one of these steps, danger, danger, danger. Okay, and we can't. So based on these things working, we can now have a new perspective on creationering and reverse engineering these things and appropriate that for creation science. So let's do that. So there's a multiscale aspect to the universe. What's God's objectives? Well, if you're Presbyterian, it's to give glory to God, honor Him in all you do. But for a Christian like me, I just go with Jesus' words when He said maximize love for Him and maximize love for others. Sorry if I offended any Prezzies on the phone call here. All right, and then there's constraints. So he made spiritual laws, physical laws. There's variables. He made elements of the periodic table. He made the souls, angels, spirit beings. And if you go down the length scales, the universe is the system. The first subsystem is the astrosphere, geosphere, biosphere. The second one in the astrosphere, you have planets, satellites, stars. The second one for geosphere is a core mantle crust. The biosphere is humans, animals, and vegetation. You go to a third subsystem. If you look at the human, your body, soul, and spirit. Soul is mind, will, emotions. You go down in each length scale. And you can go through this whole process for the astro, geo, bio, and you could say, what are the objectives, what are the constraints, what are the variables? You downscale first. All right, let's look at something here in terms of the biosphere. So in this particular thing related to creationeering and using ICME and the different length scales, the first length scale, we're going to say the biosphere. And then we're going to say, hey, let's take the human body. So that's the next subscale. And then we're going to say, hey, let's look at systems, organ. And I'm going to take the circulatory system. We're going to go one down more, and I'm going to say, hey, let's take blood. Because blood's part of the circulatory system. And then inside the blood system, I'm going to pick red blood cell. I'm going down, 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 okay? And then the component, I'm going to pick a globin inside the red blood cell. And there, the element is going to be oxygen I'm worried about. Now, let's think about this. What's the procurement? What did we have to do to get the material? We had to breathe. There had to be another system set up in this to be able to provide oxygen to the circulatory system, right? What's the logistics of this? What if I had that lung breathing system before the circulatory one or after it? So logistics is important. There's timing to this. What's your objectives? I want to minimize the time between them. I'm making these things. In assembly, I want to minimize the time of putting these things together because one won't work without the other. Symbiotic, right? Okay, what's the performance? Let's look at the performance. And when I say performance, objectives, constraints, and variables of this, of oxygen. What are we trying to do with the oxygen? Right? What am I trying to minimize or maximize with it? Right? What are its constraints? I'm trying to get it to the tissue. That's what brings life to the tissue. Is oxygen. I got to get it there to bring healing to the body. What are the constraints? Oh, it's got to fit in this piping system that has an aorta we call it a big power pump. And it goes down to the capillaries, these little pipes, right? There's constraints. There's volume size. There's amount of time. There's temperature. There's some constraints on here. What are the variables? Oh, thickness of the pipe tubes, length of the pipe tubes. There's a bunch of things in the design of making this thing, right? And there's sustainability, depth recycling. So let's take the blood one more step. Let's look at the length scales of the blood. The blood has 55% plasma, 45% solid cell. Now, I'm not worried as much about the plasma, mostly 92% water, but on the right-hand side, there's 2% of that's platelets, red blood cells 88%, white blood cells 10%. And in the 88% red blood cells, we have hemoglobin, proteins, and lipids, and the hemoglobin has the iron and oxygen. And if you look at this picture here, on the upper left, you have the blood coming through, and there's a red blood cell that has this little like indentation in the middle. And in the red blood cell, you have these 4 globins that are hemoglobins. And if you go down to the right-hand corner, you see that iron's in the middle, and you have nitrogen on each side, so it's in chemical equilibrium. And on the bottom, you have a nitrogen. But at the top, you have this thing searching for -2 electrons. And the oxygen comes in and it fits there beautifully. Fits there perfectly. And there's 4 of them. And so what happens is this whole globin and the 4 hemoglobin parts, they all start dynamically rotating and bending to bring that into structural equilibrium at a higher length scale. And all that is situated in a higher length scale in the red blood cell. And when it comes all the way down from that aorta, from the high tube down to the bottom capillary, it's changing the pressure via Bernoulli's law. And once the capillary is so small, the pressure gets increased, so much so that the pressure is so high it releases the oxygen, and it's too high and it breaks that fracture point. And then now the oxygen diffuses through the capillary into the tissue to bring life. Completely a creationeering system from all these length scales related to this. Recently, they had this thing related to football helmets. We looked at ram's horns. We studied how God designed things. We looked at woodpecker's beaks. We looked at bison hitting each other, turtle shells, armadillo shells. And there was 3 secrets in there that were revealed to us. Romans 1:20 says we can understand God's character, nature, and attributes by the things he made. So we're trying to understand the things he made to give us inspiration and revelation about the engineering, creationeering system that he made. Then, of course, once we get that, now Proverbs 8:12, as I mentioned, says, he gives knowledge for witty inventions. I was 45 years old before I asked God. I said, God, can you give me a patent? I was 45 years old before I asked that. I had no patents before that. And James had said, you have not because you ask not. So I asked, and I started getting them. They started flowing. And then from there, it's getting, okay, we're going to make this football helmet. Right now it's 15% better. We're going to try to make it, we need to make it about 50% better. And then create a company. It's your creator gives you power to make wealth. And that fulfills the Genesis 1:28 mandate that says you're to rule and reign on the earth. So that's sort of the whole picture with this and how it fits together. So in the Creationeering notes, what I want you guys to think about. First, in design, that there's objectives, constraints, and variables. Second, in those design objectives, if there's 2 or more, it demands by definition intelligence outside the system. Number 3, God created everything with a system with multiple length scales. So whatever length scale you're working at, think bigger than that. Think outside the box. Number 4, science is included in the analysis stage of the creationing paradigm. 5, when we observe something in creation now, we assume it must be the final design, whatever it is now, and thus we can apply the reverse creationeering process to study it and understand it, and understand its purpose, individually as well as the larger system. And then by conducting this creation science within the context of creationeering, we can bring more glory to God and change, I believe, human culture, particularly when we think about educating the young kids. So moving forward, my request to all of you out there, no matter what kind of scientist you are, I'm encouraging you to pray and ask about what were God's design objectives, constraints, and variables, bringing this perspective in, and insight in. You don't have to help me with K through PhD curriculum. I've got some engineering students willing to do that. If you want to challenge some people out there how to communicate things better. When we do that, number 1, I think people will realize it's not science versus faith, but science versus engineering. And that's how we want to posit it to this culture. Number 2, their own lives were engineered by the Creator himself. And by the way, I looked it up, there's about 8 million scientists in the world. There's 4 times more engineers. So I think we would have a whole bunch of people backing us up. And we won't have the fight that we had before. And that is the end of the story. So Dr. Baumgartner, please come back.
Yeah, thank you. Thank you, Mark. Thank you, Mark. That was very stimulating and pretty fast pace. Normally we have some Q&A. So we haven't gotten too many questions in the chat window. If some of you now have some questions, feel free to type them into the comment box, and we'll take some questions. Are there some questions there in your audience, Mark?
Come on up if you have it. Ready, set, go. This is a graduate student at Liberty University, Briar Walters. Briar, go ahead.
Hello. I guess my primary question would be, within creationeering, if you had to write a paper or do research within a certain field or topic, what would it be that you would be able to make a statement that says, based on this, it contradicts like the current evolutionary atheistic
paradigm?
view? Yes.
Yeah. So this is not trying to attack evolution. What I'm trying to do is just try to go after the truth. So when people made coins at the Denver Mint, they had them focus on what the actual true coin was. They didn't have them study 500 mishaps of the truth. They studied more of exactly what it was, so then they would know if something deviated from it. So what I'm just trying to do is get people to focus on that God was a creationary. He went through a process. He went through a process in Genesis 1, and I think it'll have a greater impact rather than knocking off one of evolution's thing here or there. So I haven't been thinking about that in that sense.
Thank you.
Let me pose a question. Engineers get a lot of training so that they can be good designers, that they can be effective in designing things that work. So what are there some special perspectives that somebody that goes through this type of engineering training that relate to or improve a person's ability to understand God and creation? Can you think of any ways that the typical engineer in his training has some advantage as far as understanding God and creation?
Yeah, and John, I could even let you comment. I know about your electrical engineering degree at Texas Tech, but when I went through West Virginia, High State, Stanford, Georgia Tech, most of the classes were all about analysis and looking at the detail. And I was a Christian then, and it didn't necessarily help me see the Lord, to have my mind on Him. And I think this paradigm shift, and it is a paradigm shift, I'm asking people to change the glasses by which they're looking at information and really, like Einstein said, how is God thinking? How did He think about that? And just by that framework. Now, engineers in practice do it. Like when I was working at Sandia Labs and working on the W-89 nuclear bomb, in those design phases, that's where I really learned it. There's a conceptual design, a preliminary design, a final design, and in that process, we basically went through these steps. And I was a little disappointed that my engineering curriculum didn't quite bring that out. But again, that's why we're focused on that at Liberty University. I want all these students to know the steps of these processes, so when they go in there, they have this paradigm. And my challenge to the geologists, the astrophysics, the biologists here is, there's a reason God made all these things. He made the rocks a certain way. He made the sun, a certain way related to the earth. He had objectives in all these things. And my challenge is to ask Him, to seek Him, and look it out. So it is a paradigm shift that way.
Yeah, let me, here's a question. If I can, there's a question. I'll read it. I'm interested in how God designed Earth's atmosphere as part of a self-regulating system. So, one thing generally that secular people don't normally think about is that the Earth in all its aspects are a result of design. And if there was a designer designing these systems, he would have built in stability into the system. And, in other words, that a small perturbation would not lead to some big changes and large scale instabilities, but rather than a small change, the system would naturally tend to damp that change and come back to its designed equilibrium state.
So what John's saying there again, in terms of stability, a lot of astrospheres like that. So the objective is maximizing stability. There's mathematical equations that have energy methods to come up with stability or unstable conditions. And so it's applying that math to that particular problem because He did want stable. And when I talked about errors and uncertainty, what John is saying with those tolerances, if they're staying within that, we have a reliable solution. And God made reliable solutions with the uncertainties in mind that can happen in those variations. Andrea, I appreciate your question. What I would say to you is, in terms of the Earth's atmosphere, what were the objectives? What did God try to maximize or minimize in the atmosphere? What was He trying to do? What is the atmosphere used for? How did He try to maximize or minimize? What are the constraints of it? There's obviously temperature constraints, the material constraints, and then what were the variables He had to allow to vary inside of those? So those are the first questions, Andrea. No matter what they are, what are the objectives, constraints, and variables? And that's, I hope, the takeaway point from everybody. There's a question inside here, John.
Hello, everyone.
This is Caleb Cassidy. He's a PhD student of mine working on that football helmet.
Yes, sir. Now, I do have a question related to just linking of length scales, but in terms of faith. So, taking creation science and applying it to the idea of a intelligent design that we see in the world. Now, one thing that I love is that at Clemson, where I hail from, that was not the case. Everything was more evolution-based, more scientific. There wasn't really a God in science. That's why I came to Liberty. It's wonderful. It explains a lot more to me, but I'm wondering, what is your take on the linking to the intelligent design to the Bible, specifically the Bible?
So I didn't cover today the Genesis 1 systematic review, but basically, after God, in the beginning, God created heavens and earth, and the earth was without form and void. So the first 3 days, He basically gave form to the formless. He gave structure. Day 1, He separated light from darkness. Day 2, He separated waters above, water beneath. Day 3, He separated the land from water. And then days 4 through 6 were associated with days 1 through 3. Day 4, He gave the light givers, where day 1, He gave the separated light and darkness. Day 2, when He separated waters above, waters beneath, He put the animals of the water and the sky. Day 3, when He made the land. Day 6, He gave the land animals and mankind. So in terms of days 1 through 3 structure, days 4 through 6 substance. And so there was a process there. Now, I talked about design, objectives. So there was a procurement, assembly. God's all-knowing. He does these things like this, right? He's fast. We're not fast. And He has a framework to bringing all these things together. One question is, why didn't He do it all in one day? Why did He take 6? The evolutionists say, I take millions of years, whatever. And they say, why did... And they ask, doing it in 7, He didn't do it that fast. My question is, why did He take so long? Why did He take 6? He could have done it instantly. But He didn't. He wanted a process. And He wanted a process for a reason. Actually, one of the objectives, I think, of the universe is He wants us to study it. I think one of His objectives, we weren't only made for His pleasure, Revelation says. One of the objectives is pleasure, that He made us for pleasure, and to love Him, love others, but actually to study His work, to understand the soul of God, if you will. So, in terms of Bible, the Bible doesn't specifically say design objectives, constraints, variables, blah, blah, blah. But there's pieces of this you can find. If you go through Noah's Ark, if you go through Solomon's Temple, you'll find these in there. And by the way, for everybody, I wrote a Creation and Research Society article on this that went through all these examples. Any more online?
Now looks like we've covered the main questions that people have typed in. So why don't we wrap it up now? And we thank you, Mark, for putting together such a challenging presentation, and giving us
John, I'd like to ask you a question. So, you've known me since 1991, and you came to Liberty with me, and you've sat in and heard me talk. And I've only talked about this the last 5 years. I haven't talked about this before. And so you've been going through sort of a growing process with me. So I'd like to have you share your thoughts on it. It might be a little different than mine.
Well, a major aspect of what engineers do is design things that work and are reliable, hopefully. And so most of the students have the training they get helps them become that kind of person professionally. And so they are sensitized to the issues of design, what it takes to design something well. And so that aligns. I believe that should help them be quick to recognize the design in the world around us, and especially as we're able to see what systems are like at the molecular level now. And so as far as how we package this, how we use this to communicate God as the creator, I still see that as a challenge, but it seems like is something we should be giving serious thought to. How we can use the engineering perspective to focus on the fact that everything around us is very highly optimized and designed, has the evidence of very very multi-level design at all levels. And so I think you've laid out a good challenge for how we can use this type of thinking to impact our culture. I believe we need more. We need to brainstorm more how we can be more effective.
Agreed, 100%. Well, John, I don't think there's anybody else that wants to come up and ask a question, at least in public here, and be on YouTube forever.
Okay, someone asked that you mentioned a paper that you wrote on creationeering. Somebody would like the reference to where that was published.
Yeah, it's Creation Research Society Quarterly, and I believe it's 2022. I'm not sure which volume, but in 2022. Anybody can become a member of Creation Research Society, have access to all those in the history back to 1963, by the way. And by the way, they're all cited now on Scholar Google and in ResearchGate and all that sort of thing recently.
Okay, why don't I close in a word of prayer? Heavenly Father, we thank you. We thank you for this presentation. We thank you for the challenge of reaching our world with the very important reality that you are the creator, and that the creation just screaming out, it's testifying of your power and your divine nature, as Romans 1:20 indicates. So we thank you. We thank you for Mark. Thank you for our time together, and pray you might continue to encourage us. Thank you in Jesus' name.
Amen.
So thanks,
John.
Thank you, Mark. Let's look at what we're going to do next month in August. Our speaker next month is Dr. Calvin Beisner, and I've known him for almost 20 years, and I remember about 20 years ago I read his book Between Garden and Wilderness. So his topic next time is related to that. The title is The Biblical Perspective of Environmental Stewardship, Subduing and Ruling the Earth to the Glory of God. And I think it's the benefit of man. So that should be I'm looking forward to that. Should be a very good talk next month. He is let's see, what is his title? Yeah, he's got his own organization. I'm sorry, I can't remember the name of it, but it should be an excellent talk. So thank you for your attention. We'll close for now. Bye-bye.